Okay, in this video I'm going to talk about Droz-Farny line theorem. So basically, let's say that we have a triangle, and we consider we consider the orthocenter of this triangle, like the intersection point of the altitudes, and we consider two perpendicular lines that pass through this orthocenter. So let's say this line and this line. Yeah, so these are two perpendicular lines, and we consider the segments that these two lines cut on each side of the triangles, like on the lines containing the sides. It could be the sides or the extensions of the sides. So these three segments are, so let me highlight them in blue. So this segment, and this segment. And the theorem states that the midpoints of these segments lie on the same line, so they are collinear. So this midpoint, well, in this case, like, it's not very, so the midpoint is somewhere here, so like in this case it's not very believable, but like in fact the intersection point should be probably somewhere much farther, so like much farther away, and the midpoint would be here, somewhere here, and then they would all lie on the same line. Yeah. Okay, so let's prove this theorem. So I will denote the triangle as ABC. So the midpoints. Well, the midpoints I will actually not denote anything, like I will need them only at the very end. Like when I will need them, I will denote them if needed. But for now, I don't need the midpoints. So the orthocenter is H. So let's denote the points of intersection. So this is D. This point of intersection is E. This is F. Well, let's denote them D1, E1, F1, and so this line is L1, and this line is L2. So the line L1 intersects the sides at the points D1, E1, and F1, and the line L2 intersects the sides at the points D2, E2, and F2. And so the theorem says that the midpoints of the segments D1, D2, E1, E1, E2, and F1, F2 are collinear. Yeah. So, okay, so let's prove the theorem. So the first, so I will use several other known theorems that I already proved in the previous videos. So in particular, so one of the theorems is that the reflections of the orthocenter with respect to the sides lie on the circumcircle. So let me state it. So we have a triangle, and we have the circumcircle, and we have the orthocenter here. So then the reflections of this orthocenter with respect to the sides lie on the circumcircle. So that is one theorem that I will use. Another one is that so if you have any line, and this is kind of very natural that we will use this. So if we have a line passing through the orthocenter, so now we have not only, or like I can actually reuse the same picture. So if we have a line that passes through an orthocenter, then the reflections of this line with respect to the sides, these three reflections, they are concurrent, so they intersect at a single point, and this point lies on the circumcircle. And so how to construct the reflections of the line? So like because of the first theorem about the reflections of the orthocenter itself, so let's say that we want to construct the reflections of this line with respect to BC, so like ABC. So this is the line L. We want to construct the reflection of L with respect to BC. So one point, so H, and this we denote as HA prime, right? So we construct the reflection of one point and the reflection of intersection of this line L with BC, which is mapped, like let's denote it by D. So it is mapped to itself. So D is mapped to D. In this reflection at H is mapped to HA prime. And because the like under the reflection a line is mapped to a line, so like so we know that the result of this reflection is a line, and we know 2 points, point D and point HA prime on this line. So and a line is reconstructed uniquely by two points. So therefore this resulting reflection is exactly the line HA prime D. So therefore L is mapped to HA prime D, and this is the reflection, and the same for the other two reflections. So this is the intersection point, and this is the reflection of the orthocenter. So this is the reflection of this line, and the third one, take this intersection point and the reflection. So something like this. And so, well, in this case, like the intersection point is very close to HA, like it could be like it's basically like in general it's different point. So these 3 points, these 3 lines intersect at a single point, and this point lies on the circumcircle. So now And the third theorem that I will use is Mikhail theorem. Like I will state it when I will use it. So for now we will use this. So like basically, if we go back to the original picture, so so what we have here is okay, let's draw another picture. So we have this orthocenter. We have two lines. That are perpendicular to each other. And so we consider the reflections of the orthocenter and the reflections of the line. So this line is L1 and this line is L2. We consider the reflections of the orthocenter. Yeah, so these are points. So if this is H, so this is the point HA prime, HB prime, and HC prime. So the triangle is ABC. This point is D1, E1, F1, D2, E2, F2. So and now we consider the reflections of both lines L1 and L2 with respect to the side. So this is the line, this line, this line, and this line. And so by the theorem that I just stated, these three lines must first let's denote the circumcircle. Omega, so omega is the circumcircle of the triangle ABC, right? So we know that H, from the theorem that I stated, we know that HA prime, HB prime, and HC prime lie on this omega. Now, when we draw these lines, so D1 HA prime, E1 HB prime, and F1 HC prime. So these three lines must intersect at a single point, and this point lies on the circumcircle as well. So let's denote this intersection point. So like if we draw, so somewhere here. So this is the intersection point. Okay, so H A prime is this point, and this point is P, denoted by P. So P is the intersection point of the three lines. So P is the intersection. P is intersection point of D1 HA prime, E1 HB prime, and F1 HC prime. Right, so so this intersection point, first this three, by the theorem that I stated, these three lines intersect at a single point, which we denote by P, and this point also lies on the circumcircle. Okay, so let's continue. So from the theorem that I stated previously, so we conclude that P, so these three lines intersect at a single point, and this point P, we denoted by P, this point also lies on the circumcircle of the original triangle ABC. So now now we observe that the quadrilaterals E, so let's say D1 H, D2 HA prime, D1 H, D2 HA prime is cyclic. And this is because the two opposite angles in this quadrilateral are right angles, because D2H D1 is a right angle. So let me highlight it with blue. So this quadrilateral. This quadrilateral is cyclic because HA prime is the reflection of H. So like this whole quadrilateral is symmetric with regard to the side BC, and so like the angle H in this quadrilateral is the right angle. Therefore, the opposite angle is also the right angle, and one of the criteria of a cyclic quadrilateral is that it is the sum of the opposite angles is 180 degrees. So like if the opposite angles are 90 degrees, then their sum is 180, of course. And so not only it's cyclic, but the circumcenter of this quadrilateral lies exactly at the midpoint of d1, d2. So the midpoint of d1, d2 is the center of this. So there is a circle. So let's say that omega A is the. So let's denote. So denote by omega A the circumcircle of this quadrilateral. The circumcircle of d1 H, d2 H A prime, and the center of the center of omega A is exactly the midpoint of d1, d2. So one of the midpoints that were in the problem setting. And this is because simply because of the right angles, like in a cyclic quadrilateral, like the right angle, it always subtends the diameter. So therefore d1, d2, this segment is the diameter of this circle omega 1. And so therefore the midpoint of this diameter is exactly the center of this circle. And so the same, like we do the same for the other the other two quadrilaterals. So quadrilateral E1 H E2 HP prime, this quadrilateral, and F1 H F2 HC prime. So these three quadrilaterals that I highlighted with blue, green, and yellow. So we denote the circumcircles of this quadrilateral by omega A, omega B, and omega C. So omega B is the circumcircle of the quadrilateral E1 H E2 HB prime, and omega C is the circumcircle of the quadrilateral F1 H F2 H C prime of the yellow quadrilateral. And so again similarly the centers of these circles omega B and omega C are the midpoints of the segments E1, E2 and F1, F2. So the center of omega B is the midpoint of E1, E2, and the center omega c is the midpoint of f1, f2. So now if we go back to this point P here, so now we consider the so now we will use another theorem. It's called Mikell theorem. So let me state it. So Mikell theorem, Mikell's theorem, and it says that if the so if we have a triangle and we take arbitrary points on the sides of this triangle, like 1 point on each side, and we consider the circumcircles of these triangles, this and this, then these three circles intersect at a single point. Actually the points that we pick on the sides, they could be on the extensions of the sides as well. So like if we let's say if we pick these 3 points, so something like this, then we consider the circumcircles of this this and this. Yeah, then these 3 circles must have the same, must have a common point. They must intersect at a single point. Like on this picture, it doesn't look that way, but like it's because I I didn't draw this circle correctly. So it should be more something like this. Yeah, like my picture imprecise, but so like because of that it doesn't look that they intersect at a single point, but they do. Yeah, and actually this circle as well. It should be the circumcircle of this triangle, so it must pass through and so basically the common point is most likely somewhere here. So the circumcircle passes something like this. So they would have a common point. Yeah, so we will use this theorem now here. So we will use it for the triangle. So I will highlight it in red. So we will use it for this triangle. And for the points H, HB prime, and HA prime. So what I highlighted in red. So the triangle and the points on the sides of these triangles, in this case on the extensions of the sides. All 3 points lie on the extensions of the sides. So from this Mikell theorem we conclude that the circumcircles, so let's write this carefully. So let's write it here. So the circumcircles of these three triangles must intersect at a single point. So, like for the triangles, we pick the vertex of the red triangle, one vertex of this red triangle, and two red points on the opposite sides. So, not on the opposite side, but on the sides that pass through this vertex. So, like we pick the point P, and then we must pick the points H, B prime, H, A prime. This is one triangle. Then the second one would be D1 H, A prime, and the third one is E1 H, B prime. So the circumcircles of these three triangles must intersect at a single point. So now let's figure out what these circles are. So the triangle PHB prime HA prime. So this is actually this circle is actually omega. The circumcircle of this triangle is omega because we know that P lies on omega, and HB prime and HA prime lie on omega, like from this theorem, right? The reflections of the orthocenter with respect to the sides lie on the circumcircle of the original triangle. So the points HA prime and HB prime also lie on omega. So the circumcircle of this triangle is exactly omega. Now the circumcircle of DHHA prime, D1HHA prime. What is this? So D1 HHA prime. So these 3 points lie on the are in this in this quadrilateral, like in this quadrilateral. That we proved that it is cyclic, and so therefore the circumcircle of this triangle is the same as the circumcircle of this whole quadrilateral, which is omega 1, or omega A. So the circumcircle of this quadrilateral is omega A, and the circumcircle of this quadrilateral E1 H HB prime. So again, E1 H HB prime. So these are 3 points in the green quadrilateral. Green quadrilateral is the cyclic quadrilateral, and its circumcircle was denoted by omega B. This one. So this is omega B. So what we proved now by Miquel theorem is that these 3 circles, omega A and omega B, intersect at a single point, right? So intersect at a single point. So omega A and omega B, they already have 1 point in common, which is H. But we know that that H is not this common point of all these 3 circles, because H does not lie on omega, right? omega, the circumcircle of the original triangle ABC does not pass through the orthocenter, obviously. So this is not point H. So the second point of intersection of omega A and omega B, so omega A and omega B, these two circles. So let's draw them separately. So this is, let's say, is omega A, and this is omega B. So they already have one point is common, which is H. So, and we proved that these three circles have a common point. So therefore this common point is the second point of intersection of these two circles. So let's denote this point by Q. So denote this point by Q. At a single point, denote it by Q. Denote it by Q. So this is the point Q that is the second point of intersection of omega A and omega B. And it is also the, like it also lies on omega. So somewhere here passes omega, capital omega, like. Right, so Q belongs to omega A, omega B, and omega. Yeah, so also notice that the intersection points between omega and omega B, so this second intersection, so like if you draw this other intersection point, so this is point H HA prime, and this is point HB prime, because HA prime lies on both omega A and on omega, and HB prime lies on both omega B and on omega, capital omega. So this is basically the picture that we have. So Q is the is different. So because we know that omega A does not pass through HA prime, so the Q is also the second point of intersection of omega, capital omega, and omega B. So, and similarly for the HB prime. So we know basically all points of intersections of these three circles. Yeah, so similarly we construct the same picture for the other circles. So we consider now, instead of this red triangle, we consider now another basically red triangle. So we consider the points so for the triangle P E1 F1. So yeah, I ran out of colors, but anyway, so like, okay, let's remove this red triangle. So Now we consider this red triangle. This red triangle and the corresponding points H, HB prime and HC prime. And again write the Michel's theorem. Michel's theorem for this red triangle and these points, these red points. So basically, like we can do it, but we can simply say that because we picked the two of them, out of these three points, HA prime and HB prime and HC prime, we picked two of them arbitrarily, so without loss of generality. Basically by similar argument we will obtain the similar result. So the similar result would be that the circles omega B and omega C would intersect at a single point. So if you write the Michel's theorem for this now red triangle and these three red points, we would get this, that capital omega B and omega C, they intersect at a single point. Intersect at a single point. And similarly for the third triangle, we would get that omega C and omega A intersect at a single point. So from these three results, basically we see that so what can be this point? So the point of intersection of omega B and omega C. So we know already that omega and omega B, like from this picture, so this is omega and this is omega B, right? They already intersected 2 points, HA prime and Q, right? So we know that this point of intersection cannot be HA prime because omega C doesn't pass through HA prime. So the only possibility is that it's this point Q. So basically they intersect at a single point. So basically, because in these three circles and in these three circles we have two of them common, so omega B and omega B and omega. So the only possibility for these intersection points could be the intersection points of these two circles, which are 2 points, and one of them does not pass through the third one, through the third circle. So the only possibility that this point is Q. This point is Q, the same point of intersection of the first three circles. And for the third triple of circles, the point of intersection is also Q. This point is Q. So this is the same point for all these three triples of circles. So basically the picture that we must draw is that there is the third circle omega C. It looks something like this. It also pass through H because all of them pass through H, right? So through H, through Q, which we just proved that all of this circle pass through the same point Q, and another point of intersection between capital omega and so this circle is omega C and omega C, so this point is HC prime. So the picture is something like this, but so basically what we now get, the main result is that the circles omega A, omega B and omega C, they have the same 2 points of intersection. So they both, like all three circles contain, so the points H and Q, both of these points, lie on all three of these circles. So this is the main result. And the main point is that so all these three circles have the same intersection points between each other. And what this means is that the centers of these circles. So let's draw another picture, because capital omega we now don't need. So basically we have omega A, omega B, something like this, and omega C, something like this. So omega A, omega B, and omega C. So this is H, and this is Q. So the centers, like if we have two circles that are intersected 2 points, so the line of centers, the line connecting the centers of these two circles are always perpendicular to the common chord, to the common. So the common chord is here unique for all three circles. So therefore the line of centers. So let's denote the centers as MB, MA, and MC. Right. So MA. So we know that the MA, MB, the line connecting these two circles, is perpendicular to HQ. The line MBMC is perpendicular to the same common chord HQ, and the third line connecting the centers MCMA is also perpendicular to HQ. Not just perpendicular, but perpendicular and passing through the midpoints of HQ. So perpendicular and so if we denote the midpoint of HQ as M, so then also like M belongs to MA. Okay, let's write it differently. So so the line of centers is the line of centers between two circles is the perpendicular bisector of the common chord, right? So it's not just perpendicular to the common chord, it's the perpendicular bisector of the common chord, right? So therefore MAMB is, this line MAMB is the perpendicular bisector of the line of the segment HQ, and the same for these two lines. So all three of them are the perpendicular bisector of the same segment HQ, right? So MBMC is also the perpendicular bisector, and MAMC is also the perpendicular bisector. So therefore, from this, it implies that it is the same line. So MA, MB, and MC are collinear. So all three centers of these circles, omega A, omega B, and omega C, they are collinear. And this is exactly what we needed to prove. Because the centers of these circles, omega B and omega C and omega A, they are exactly the midpoint. So the center of omega A is the midpoint of the segment D1, D2. The center of omega B is the midpoint of E1, E2, and the center of omega C is the midpoint of F1, F2. So, and these are exactly the midpoints that we needed to prove that are collinear. So we needed to prove that the midpoints of the segments D1, D2, E1, E2, and F1, F2 are collinear, and that's exactly what we proved. So the centers of the circles omega A, omega B, and omega C are exactly the midpoints of D1, D2, E1, E2, and F1, F2. So these three centers are denoted here by MA, MB, and MC, and we proved that they are collinear. So this concludes the proof.